Okay, that is something to bear in mind. The next thing I would like to draw your attention to is the following. Remember that when you plot a transfer function of this sort, I mean basically this is a complex number, S is a complex number, and therefore this is also a complex number, and has both a real part and an imaginary part. And let us assume that P1 and P1 star are the poles of the system. So, if I plot the real part of S and the imaginary part of S on a sheet of paper and plot the magnitude on the z axis, right, I will basically get a, I mean it is basically a 3-dimensional plot, correct, and if and the pole is somewhere on the xy plane. If I draw the pole, that is the pole, and that distance happens to be, what is that distance? It is omega naught by 2q, and the length of the arrow from the origin to the x is basically omega, correct. Now, if I look at a 3D plot, how will the magnitude plot look like? Pardon? It will tend to infinity at the pole, right, and so if you and if basically if you have a filter transfer function with a whole bunch of poles, at each of these points basically you will see what you will see is Mount Everest, right, okay, and but when you evaluate h of j omega, what exactly are we doing on this picture? If we are evaluating modulus of h of j omega, what would you do on this picture? You take this 3D plot, right, the surface, and slice it along the j omega axis and look at the profile of that slice as seen from whichever side that you want, alright. So, if you do that, then you will basically see mod h of j omega, right. So, mod h of j omega is simply nothing but mod of h of s evaluated at s equal to j omega. In other words, you travel along the j omega axis and then keep evaluating h of s. Pictorially, you take the 3D plot and then slice it on the j omega axis. Alright. So, these are simply things that you bear in mind, right, and what comment can you make about let's consider only that you had only this pole called this P1. At what frequency do you think the gain will become very large as you keep going along the j omega axis? At what frequency do you think you should expect to see a peak in the magnitude response? Pardon? Close to omega, I mean somewhere in that region, and why does that make intuitive sense? At P1, so what? But we are not evaluating it at P1, right? Pardon? Yeah, very good, right. So, remember that as this again from pole 0 plots in your networks and systems class or electric circuits and networks class. If you want to evaluate if you had a transfer function and you want to evaluate h of j omega at some s, what would you do? You basically draw arrows from, is this familiar to you guys? So, let us say you have a transfer function 1 over s plus P1 and you want to find h of s at some frequency s. in the complex plane. What do you do? This is the complex plane looking from the top. Let us say you want to evaluate, this is say some P1. If you want to find h of s, what would you do? At this point, let us say you want to find h of s, where s is that point marked there. What would you do? You will draw vectors from origin. From s, this is nothing, simply the length of the complex number, right. So, that is this guy here, right, and you do it to all the poles, and then you do it to all the zeros, and then the magnitude response is the ratio of the vectors all going from that point to all the zeros divided by the vector going to all the poles, right. I hope this is familiar, okay. And so, therefore, if you are evaluating stuff on the j omega axis, it must follow that at every point on the j omega axis, you would draw these vectors from that j omega to all the poles, right. And in this region, which pole has the maximum influence on the magnitude response? P1. Why? Very good. That is because the at this j omega, for instance, the arrow that goes from that point to the pole is the shortest, and the response is 1 over the length of that that arrow, and therefore, in that region you can see that the length changes most rapidly, and therefore, you should expect to see that pole has the maximum influence on the magnitude response in that when you evaluate the frequency response over that region. Does it make sense? All right. Okay. So, with all this background information, let us see what happens to the behavior of our integrator. So, let us say this is R and this is C, this is Vi and this is Vo. All right. So, what is the what is the ideal response, of course, is minus 1 by SCR. And now, the gain of the op amp is omega u over S. Okay. So, what comment can we make about the transfer function? There is no other way except to simply evaluate it. So, what do? What is this voltage? Please sit and evaluate it. Yes, can we put this in the form 1 by SCR times some other transfer function, and the idea is that if omega u tends to infinity, this should tend to 1, okay. Mm-hmm. Mm-hmm. Plus 1 let's use omega u. Remember that 1 by RC is nothing but omega naught. That's the center frequency of the okay, so fine, go ahead. Omega naught by omega u. Minus 1. What's happening, people? You can't get minus 1. I think there's an no. I'm getting more answers than there are people. Alfred, what do you think is the correct answer? Is right? I want somebody to confirm because we don't want to go in to do a whole lot of math and then find out that the basic thing is wrong. Can somebody else confirm that this is correct? Overall minus should be there, no? I mean, this is equivalent to putting a minus here, if that's what you guys are saying. Okay, let's go through the steps. So let's see where we have made a mistake if we have. This voltage is nothing but, is this correct? Let's go step by step. Is that correct? It's simply, it's a potential divider, correct? So, the voltage in the middle is simply Vi times this conductance. G is nothing but 1 by R times plus Vo times Sc, which is the conductance of that arm, divided by the sum of the conductances, right? That multiplied by minus omega u by S must be equal to V naught. So, this seems okay, alright. And now, I will just simply take S over omega u to that side and then move the V naught times Sc by G plus Sc, which is a negative sign. I will move it to the right side, it just becomes positive. So, this is fine, this is fine, and this must be equal to minus Vi times G by G plus Sc. This is correct? Okay. So, now I just group these terms, which is S over omega u plus 1 over 1 plus G by Sc, which is nothing but 1 over SCR, correct? And this is minus Vi over 1 plus SCR. So, this is also okay. Yes. Okay. So, Vo by Vo by minus Vi is nothing but one by 1 plus SCR times 1 over, this becomes a denominator here, 1 over S over omega u plus SCR by SCR plus 1. Okay. Now, all I am saying is that let us try and isolate this 1 by SCR, so that whatever else we have, okay, hopefully becomes a constant as omega u tends to, it should tend to, I mean, as omega u tends to infinity, what would we expect to get C for the transfer function? Minus 1 by SCR, right. So, this is the ideal transfer function, and the rest of it is simply a factor which causes a deviation from the ideal transfer function. and therefore, as omega u tends to infinity, we should make that should go to 1. All right. Okay. So, what is that factor is what I am trying to get from you people. So, what is that factor now? Plus omega naught by omega u plus, pardon? Minus v naught by vi, right? Okay, so can somebody else confirm? Very good. Okay, so hopefully we have our math right. Vo by vi of s therefore is minus 1 over SCR times this transfer function, which is 1 plus omega naught over omega u plus s over omega. Intuitively, what would you expect for omega u versus versus omega naught? What do you think we should have? Well, you basically are trying to make an integrator with a unity gain frequency of 1 by RC, which is omega naught, okay, and this is working on the principle of negative feedback. So, at all frequencies of interest, where is our integrator? Okay, at all frequencies, this will work like a good integrator if that voltage is at virtual, if that is a virtual ground. That will only happen if the gain of the integrator is ideally infinite, in practice very large. The question is, over what range of frequencies should that gain be very large, okay? And what comment can you make? Well, at least at frequencies much greater than omega naught, up to frequencies much higher than omega naught, you expect that the op amp has got a sufficiently large gain so that virtual ground voltage is sufficiently. The reason why that virtual ground voltage is small is because the gain of the op amp is very high, correct? So, if you want this to work like a good integrator over a frequency range, up to at least up to omega naught, and obviously including frequency is much higher than omega naught, then over that range of frequencies you must ensure that the gain of the op amp, which is what would be the gain of the op amp at a frequency omega naught? What would it be? The magnitude of the gain would be omega u over omega naught, right? That number better be much larger than 1, correct? So, therefore the concept the argument therefore is that omega naught by omega u, without even going further, must be a number which is, what comment can we make about omega naught over omega u in comparison with 1? Much smaller than 1, correct? So, therefore, you can approximate this as minus 1 by SCR, correct, divided by 1 plus S over . Okay. So, does this make, why does this make intuitive sense? Of course, this comes out of the math, but why does this make intuitive sense? All right. So, all right, at high frequency, which of these elements, and what happens to the capacitor? The capacitor is a short circuit, right? So, what kind of, what comment can we make about the loop gain around the op amp? The capacitor is a short circuit, what happens? What comment can we make about the feedback factor? It is 1, right? If the feedback factor is 1, right, what comment can you make about the closed loop pole? The open loop pole is omega u by, the forward amplifier, so to speak, has got a transfer function omega u by s. The feedback factor is 1. So, what comment can you make about the closed loop bandwidth? It is simply the unity gain bandwidth of the op amp, alright, and that is what this is telling us. It is telling us that at very, very high frequency, basically the behavior must eventually have a pole at omega u. This is clear, people, alright. So, in English what this means is that, well, the op amp is not infinitely fast, right, it takes some time to react, and as a result, what comment can we make about the integration? If you had an ideal integrator, if you put a step, you should get a what kind of transient? If you put a step in an ideal integrator, what will you get at the output? You will get a ramp, alright. Now, if you have an integrator like this, okay, well, where it has got some integration, but it's also got an extra pole, right. What comment can you make about the output response when you put in a step? So, I am going to draw the negative of the waveform to avoid the minus signs. So, ideal integrator is you put a step and you get a ramp, alright, and what is the slope of the ramp? 1 by RC, this is the ideal one, right, okay. Now, but we have this extra character here, so what comment can you make about the response? It is like taking this and passing it through a low pass filter 1 by 1 plus s by omega u, right, and that therefore will cause an output which basically does something like this, right, okay. And what will be the delay? 1 by omega, right. So, in other words, the integrator which was ideally supposed to give you the integrated output waveform right away, correct, now has a within quotes small delay, right, and that delay is because, well, the op amp is not fast enough, alright. Okay, before we go ahead and start doing the math on what this delay does to our transfer function, intuitively what should you expect? What do you think will happen to the transfer function of this filter if every integrator, I mean, let us assume for the time being that this op amp is ideal, so that you do not have to worry about the delay there, there will be delay there also, but okay. The integrator, both these integrators, they do integrate, but they add a little bit of delay. So, what comment can you make about the poles of the close of this system? And why? I mean, yeah, eventually everything is because of non-ideality of the amplifier, right, but I am asking you, pardon? Very good. So, basically as you can see here, this is a feedback system, right, you have an integrator and then you have another integrator and then the output is fed back, right. If you have a feedback system and then you introduce, now each of these building blocks has got some delay. So, if you have a feedback system and then you introduce delay into the feedback loop, what comment can you make about the nature of the closed loop transfer function? If you have a feedback loop and you add a lot of delay into it, what will happen? It will tend to become, it will tend to become unstable, or it will become closer to getting unstable, right. So, in the parlance of poles and quality factor and so on, what comment can we make about what should we expect before doing the math? If our op amps are non-ideal and have some delay associated with them, the integrators also have delay associated with them. They are now embedded inside this negative feedback loop. Earlier, without delay, the quality factor of the poles was something. And what is the quality factor, the interpretation of the quality factor? It is how close those poles are to the edge of instability, right. Now, because there is delay, what happens? Does the system tend to become more stable or more unstable? it's inching towards instability. If you go on increasing the delay, we are almost sure that this will become unstable. So, the poles therefore must be inching closer to the edge of instability. So, what comment can we make about the quality factor? We should expect the quality factor to increase. Does it make sense, people? Alright.